Alright, in this video I'm going to introduce you to a conceptual problem solving method that we're going to use often throughout this course. One of the things that AP questions like to focus on are your ability to understand relationships between different situations by comparing the equations and variables in variable form as opposed to just solving something using numbers. So let's read the problem. Jack and Jill go up a hill to fetch a pail of water. But before they fall, unlike the fairy tale, Jill accelerates up the hill at a constant rate that is double that of Jack. So the first bit of information is we know it's constant acceleration, and Jill's acceleration, so the acceleration of Jill is double the acceleration of Jack. So by how much faster does Jill make it up the hill relative to Jack? So we want to know what is Jill's time relative to Jack's time. So Jill's time will be some proportion different from Jack's time because she's accelerating faster. So in order to solve this, we need some more information. We can assume they both travel the same distance up the hill. So my delta x for Jack and my delta x for Jill will be the same, which I'll just call delta x. And they both start at rest. So V naught for Jack is equal to V naught for Jill, which is equal to V naught. It says use variables only to solve for Jill's time relative to Jack. So what we need to do is find an equation that relates the acceleration of Jack and Jill's, the time, and the displacement. So it has to include those variables, and I'm going to show you how we can use a ratio to solve this pretty quickly. So let's look at our constant acceleration equations. The first one is not going to work because we don't know final velocities. We have no information about that. The second one, since we know V naught is 0, that goes away. We know delta x's are the same. We're going to compare times using accelerations. So this is a winner. So we have variables that we can compare. So the first thing we want to do is write an expression for Jack's displacement and Jill's displacement. So basically write the second equation out for each of their two motions. So delta x, and I'm just going to call this delta x because I know these are the same. So delta x, this will be for, let's do, I guess it doesn't matter. Let's do Jack first. So delta x equals, now we know V naught is 0, so V naught t goes away, and we have 1/2 the acceleration of Jack times the time of Jack squared. So that will define, if we knew Jack's time up the hill and his acceleration, we could find his displacement. So then we're going to do Jill below it. Delta x equals 1/2 the acceleration of Jill times the time of Jill squared. So again, if we knew Jill's acceleration and her time, we could find the displacement. But we want to find relative one value, one time relative to the other. So I'm going to use this expression at this point to eliminate one of my accelerations. I know that Jill's acceleration is double Jack's. So instead of Jill's acceleration, I'm going to insert here 2 times Jack's acceleration. So this is helpful because it eliminates a variable. And now when I do a ratio between these two, what you'll see is everything cancels out other than the times that we're looking to compare, because now our displacements are the same and our accelerations are in the same terms, and the only thing that's not the same are the times. Now you could do substitution. You could express one value for, express this formula in terms of AK, substitute it in here, or set them equal to each other and solve it, since these are the same, so you can set these equal and cancel it all out. But a ratio method is a good way, especially when we have some squares, to quickly eliminate certain variables. So when I set these up as a ratio, what I'm left with is delta x over delta x on the left. Well, these basically cancel and give me 1. My 1/2 on this side are common and cancel. My AKs are common and cancel. And what I'm left with on the top is delta TK squared over 2 times delta TL squared. All right, so very quickly in one step with the ratio, I've eliminated many of the variables. So I want to get an expression for TL, Jill's time, relative to Jack's. So let me, at this point, multiply delta TL squared over excuse me to the left, and then I have 1/2 and 1, so I have a square term here, so I'm going to have to square root this. Okay, so what I end up with is Jill's time is going to be square root of 1/2 times the delta T for Jack. I could also express this in terms of Jack. I can multiply or divide by square root of 1 over 2, divide by square root of 1 over 2, which would give me root 2. I could say Jack's time would be square root of 2 longer than Jill's time. So if you notice in what I've done here, I've solved the problem without using numbers by setting up expressions for the two different motions, finding a common formula that includes the variables that we know that are equal and things that we know we want to compare, and then by just dividing them by each other and simplifying them so that I get one expressed in terms of the other. And this is how we use the ratio method for solving conceptual problems.